In most VP stages, the number of pixels far exceed that of your computer monitor at home. Although you're getting fantastic real-time results on your desktop, it's typically not going to be the case on a stage. Due to this, the rendering workload has to be split between many servers. This is called cluster rendering. The challenge is, how do all these machines work together to create a single cohesive frame? And how can we increase performance while reducing the overhead of managing all of these render nodes? The scale of productions today require more and more horsepower. Larger stages simply have more pixels, and even in smaller stages, the requirement for more photoreal content can drive up the need for more render nodes. Disguise's RenderStream is a render platform designed to do exactly that. Let's get into a few specific things that make it super ideal for VP today. Let's start with running Unreal Engine on RenderStream. Unreal's nDisplay is already a powerful tool for cluster rendering, and it's further enhanced by RenderStream in the following ways. Asynchronous rendering. In a typical nDisplay setup, the many render nodes have to synchronize with one another. This is a critical piece as each node is rendering portions of the frame, and we want those portions to be of the same frame and not the frame before or after. In addition to the rendering, there are a few other things that need to happen before that frame could be sent to the LED wall. Things like mapping, warping, and compositing. RenderStream architecture requires synchronization at only the compositing stage, not during render. To keep latency low, the nodes are sent render requests asynchronously, meaning on their own clock, and some come back with renders faster than others. RenderStream takes advantage of the time between frames, so you're not waiting for a clock to tick, which in VP can be as long as 42 milliseconds before processing an incoming data stream. For computers, 42 milliseconds is a long time to wait around. The resulting frame is glued back together by the main compositing server, either the VX or the GX, which is not part of the render node system. By essentially having a supervisor who makes things align after the render, the need for complex wiring and genlocking every single machine is mitigated. Only this final step needs synchronization. Keep in mind that this data is traveling on an incredibly high-speed fiber network of up to 100 gigabytes per second that is purpose-built for this. You may think this adds more latency, however, due to the clever architecture and the design of the system, the latency results from RenderStream are equivalent to nDisplay. The benefit is, overall system integration is far easier and you can control every aspect of your stage from a single point. When the rendering muscle is separated from the brain, this truly unlocks operational capability on a daily basis. Now, the type of content engine doesn't bind you to a specific workflow. It's a single workflow for all types of content. Temporal spatial compensation. Because a disguise system has complete awareness of all the subsystems in a volume like camera tracking, LED processor, render nodes, and fiber network, it has an accurate view of the overall latency from camera move to the LED wall refresh. Disguise can take this latency and make the user feel more nimble. Let me explain. Actual latency is cumulative delay in rendering, camera tracking, projection, and so on. All of this together, this is a firm number. However, if the rendered frame is decoupled from projecting those frames onto the LED wall, you can do something really interesting. As the render frame from the past come in, you can reproject it slightly in the direction of the current camera position, giving you the perception that the latency is now reduced. Only a few frames of compensation is all it takes to make the camera feel more snappy. That's exactly what happens in RenderStream. Because the compositing is separate from the render, Disguise can update the reprojection based on the current camera position rather than the position when the render was initiated. This reduces perceived latency, the lag you'd feel when you're making a camera move. To the cinematographer on set, they can make quicker and more responsive moves without worrying about how all this stuff works under the hood. Render flexibility. Let's face it, the system that is the most flexible, that could do the most amount of things, can benefit the studio from a business perspective. If you can focus all of your rendering power on the inner frustum, then you are getting the best return on investment on your rendering system as far as placing image quality into what that camera captures on sensor. What if you could just point a few render nodes to render that really complex object that has to look highly photoreal? Well, you can now easily do just that. How about separating the rendering power by foreground, midground, and background? you can do that as well. The more levers you have to pull, the more efficient the rendering stack becomes, meaning your investment is able to see its full potential. This is all done with the click of a button, without actual rewiring or restacking hardware. Lastly, RenderStream is an open and agnostic platform. So if you have an upcoming content tech that needs to run in an LED volume, you can program it to harness all of this rendering power. An example of this is Volinga, who are harnessing RenderStream to power real-time Gaussian splats for LED volumes. There's already support for content engines like Notch, Touch Designer, Unity as well, and more coming soon. RenderStream directly empowers content flexibility. The ease of choosing the type of content engine for your virtual production shot, all from a single system. This covers RenderStream in a nutshell and why I believe this is the best way to render real-time content for VP. If you have questions or comments, let me know and I'll be happy to answer them. Thank you for watching.